Hello guys, my name is Derek Trina.
My name is Josh Saldana.
My name is Demetrius Sanford.
And today we're talking about electric fields in a sphere and a cylinder.
Before we begin, we must first know these given formulas in order to find the electric field of a sphere and cylinder. For starters, we know that Q enclosed is the integral of rho dV, where rho equals to rho naught r to the power of n. Using this equation, we can find Gauss's law, which is Q enclosed over E naught. Furthermore, we must also know the area of a sphere, which is 4 pi r squared, and the area for a cylinder, which is 2 pi rl. Let's begin with a sphere. Using the formula Q enclosed equals the integral of rho dV, we can plug in rho naught r to the power of n for rho, and we can also add the area of a sphere. Since 4 pi rho naught is a constant, we move it outside of the integral, which will result in being equal to 4 pi rho naught, the integral going from 0 to r to the power of n plus 2 dr, where n is given in a problem, and the plus 2 is from the r squared from the area. Using Gauss's law, we get Q enclosed equals 4 pi rho naught r to the power n plus 3 over n plus 3, where the 3 comes from the integral of r to the n plus 2. This is for the electrical field for the inside of a sphere. Using the same equation, we can find the electrical field outside of the sphere, where r is replaced with a. Just like the electric field of a sphere, the electric field of a cylinder is very similar. The only thing that changes is the area, which in this case is 2 pi L. Using the same equation as the last problem, we get Q enclosed equals the integral of rho dV, where we plug in rho and we also add the area of a cylinder. Since 2 pi rho naught L is a constant, we move it outside of the integral, which will result in being equal to 2 pi rho naught L, the integral going from 0 to r, and then r to the power n plus 1. As you can see, it's very similar as the last problem and can be followed with the same steps. Now let's move to a live demonstration of these concepts.
Hi, my name is Josh Saldana, and we're going to be working with the electric field of a sphere. First, we drew out the schematic of the sphere, analyzing the points of interest. What we're giving already from the problem was rho equals rho naught r cubed. Now from there we have to find where r is less than a, r is greater than a, and r is equal to a. And to begin it all, we need to find the Q enclosed. So from the equation we have Q enclosed equals integral of P dV. And from there we just broke it down further. From Q enclosed to equals the integral of rho naught r cubed times 4 pi r squared. The 4 pi r squared is the area of the sphere given. And from there, we just continuously broke it down to find the cube total, which would end up to being 4 pi rho naught a to the 6th over 6. From here, we have r is less than a. From here, we got integral of e times dr equals q enclosed over e naught. And following the equation, we have e times 4 pi r squared, again the area of the sphere, equals 4 pi rho naught r to the 4th or over 6 e naught. What we did right here is cancel out the 4 pi r squared and cancel out the 4 pi here and reduce the 4 from the 6 to a 4 as it would have been 6 originally. And from there we just we solved it and we got e times r less than a equals rho naught r to the 4th or over 6 e naught. Following the same instructions from here, we did the same process of canceling like the units that were the same. So here it was where it's 4 r greater than a, it's e times 4 pi r squared again equals 4 pi rho naught a to 6 over 6 e naught. Again, we just canceled out all the following 4 pi, and we just left that alone. The reason why we didn't cancel out r squared because we needed down here for the further equation, which is e is r greater than a equals rho naught a to 6 over 6 e naught times 1 over r squared. Finally, we have r equals a, which is in the equation. Again, we're following the same steps as before. We have e times 4 pi r squared equals 4 pi rho naught a to the 6 over 6 e naught. what we did here, again, cancel the following equation with the given 4 pi was canceled out, r squared was canceled out, and we got 4. So finally we have E, r equals A equals rho naught A to the 4 over 6 E naught.
Alright, so I'm going to be explaining the electric field of the cylinder. So this is the equation we're given rho equals rho naught R. So we have to find R less than A, R greater than A, and R equal to A. So we start off here with like Q enclosed equals rho dV. So Q enclosed equals rho naught R times 2 pi RL, which will give you 2 pi L rho naught to the integral of R squared. So then that's how you get your Q enclosed and your Q total. So from there, you plug that into the equation, the integral of EdA equals Q enclosed over epsilon naught. And then from there you will get E times 2 pi RL equals 2 pi L rho naught R Q over 3 epsilon naught. When you simplify that, you will get R less than A equals rho naught R squared over 3 epsilon naught. So then, I simplified this over here so I didn't have to do all the work. But R greater than A, you will have 2 pi RL equals 2 pi L rho naught A squared over 3 epsilon naught. And then that's R greater than A equals rho naught A squared over 3 epsilon naught times 1 over R. And then for R equals to A, is pretty much the same thing as this one over here, R less than A. But E times R, even R equals A, is rho naught A squared over 3 epsilon naught. And that is how you find the electric field of a cylinder for when R is less than A, greater than A, and equal to A.